Okay, the objective of this screencast is to derive and in the process conceptually explain the origin of the Gibbs equation, which you see before you, and which, as we have repeatedly mentioned and at times discussed, is the origin of a very large fraction of what we know about energetics and biochemistry, cell biology, and many areas of chemistry and some other areas of science. And so if you have probably seen this many times in one form or another, most likely you first saw it as delta G free energy equals negative RT ln K, where K is the equilibrium constant, but the dissociation constant, as we have covered before, is the reciprocal of an equilibrium constant, so that gets rid of the negative sign. And so in biochemistry, this would be the most commonly used form of the Gibbs equation. And if you look at it naively, it says something absolutely remarkable, which is that free energy, which naively is energy, can somehow be measured via concentration, right? Because dissociation constant is fundamentally a measurement. Determining a dissociation constant fundamentally involves measuring concentrations at equilibrium. So this comes from a concentration measurement. And this equation naively says you can determine energy from measuring concentrations, the number of molecules you have per unit volume in some physical system. So that is quite remarkable. Of course, one component, a central point of how that works, is that free energy in the end is not really measuring energy. It does reflect the amount of Newtonian energy that is free to do work, meaning the maximum amount of Newtonian work that can be done coupled to a chemical reaction or some other physical process. And so it does have a meaning in terms of actual Newtonian energy, which is the energy available to do work. But in thermodynamics, the free energy, of course, is used for many, many things beyond figuring out how much mechanical work can be done by a system. And of course, it is the most important factor, whatever point about it, is that it will determine the direction of a spontaneous change. And because equilibrium involves spontaneous change proceeding in one direction until it is exactly balanced with the tendency to go in the other direction, equilibrium is essentially a systematic absence of spontaneous change, and therefore the equilibrium point is also determined quantitatively by the second law of thermodynamics, meaning where the entropy of the system is maximized. And so given that spontaneous change cannot be the direction of spontaneous change and the equilibrium point where spontaneous change reaches a stable state, neither of those things can be determined by Newtonian energy because Newtonian energy is conserved. You can couple a chemical reaction to doing external work. At that point, the free energy captures the amount of Newtonian energy, maximum amount of Newtonian energy, maximum amount of Newtonian work that can be done. But more fundamentally, it is describing the direction of spontaneous change and the balance point where spontaneous changes hit basically equilibrium. And therefore, it is fundamentally about entropy, and free energy is fundamentally a measure of entropy, as we have said before. It is called free energy because that is factually accurate. That is the energy, Newtonian energy available to do work, coupled to some chemical reaction. But more broadly, really what's going on is entropy units are weird and hard to specify. Energy units are widely used, objective, and sort of easy to understand and specify. And so mostly what's going on with the free energy is that it is expressing entropy in terms of energy. And we'll see exactly how that relationship, we've talked about it before, but I will reiterate exactly how and where that relationship comes from. All right, so that's our goal, is to go from beginning to end, really first principles, some slightly more, maybe something a bit beyond first principles, because the second law of thermodynamics well, and it is a absolutely fundamental principle. So I suppose you could call it a first principle. I guess it is not what comes to most people's minds as a first principle. It also took millennia for people to sort of figure this whole thing out. But in any event, armed with the Clausius conjecture and the second law of thermodynamics, other than that, we're going to derive this equation from first principles. So to do that, I'm actually going to begin by stepping back a slide in the slide deck, start with the simple algebraic underpinnings of free energy. So first, we're going to look at what is free energy. Where does that come from? So the second law of thermodynamics says that delta S must be greater than 0 for spontaneous change, for some physical system change to happen spontaneously. Okay, so let's assume we are in biochemistry. We're still doing chemistry, and so we're going to take as our canonical example or our focus for developing these equations. We are going to take as a biochemical reaction, basically. And let's assume that reaction releases heat and does work. So, right, we've talked repeatedly about how heat can be released in the course of a binding action or absorbed. And the simplest way for that happened is for two things that have opposite charge to come together and interact electrostatically, or simply for two atoms that to come into van der Waals contact and go to a lower electrostatic potential energy state. When the reactants go to a lower electrostatic potential energy state, energy is conserved. That energy will be released as heat. Well, when heat is released, of course, all of this in the end will go in both directions, but we're going to focus on we're just in the course of the derivation. We want to be concrete, and so we're going to just assume that the reaction we're talking about is releasing heat, although the algebra in the end will work the other way around. But just to focus on the concepts involved, let's say the reaction is releasing heat, and so that means its enthalpy, and therefore its enthalpy, which is symbolized by delta H0, is less than 0. So it is a negative enthalpy corresponds to a release of heat. Let's say in addition to the release of heat, that reaction is coupled to doing some work. Now, this is a point of considerable, if not confusion, let's say, I don't know, confusion, misunderstanding aren't quite the right words, but this is something that can be hard to wrap your mind around. I think that's probably the best way to say it. The chemical reactions can be coupled to thermodynamic work of many kinds. As we go forward, we are going to be considering different kinds of chemical work. Different kinds of work. Thermodynamically, there are all sorts of different kinds of work that can be done. The Carnot cycle looks at work being done by gases being compressed and expanded. That is way more confusing and difficult to wrap your mind around than this. I think it's quite unfortunate that most thermodynamics courses start with that because it is just fundamentally more complicated than what we're about to do here. But it does make I'm alluding to that because it does make the point that in addition to chemical work, chemical reactions can be coupled to various kinds of mechanical work. Moving a piston using gas pressure would be a kind of mechanical work. In biology, one useful reference point for that would be the muscle contraction, and particularly the role that myosin plays in muscle contraction. The main thing that's happening when your muscles contract and you're physically moving things with your muscles, right? And that itself is mechanical work because your arm goes from rest to moving as the muscle activates, so that is clearly work. Furthermore, you can, for instance, lift a weight, and in that case, ultimately, the work required to move the weight against the force of gravity is being done by the ATP interaction with myosin. And particularly what's going on there is when ATP binds to a domain-domain interface in myosin, it closes what is essentially a microscopic clamp. It is formed by the protein, and there is literally a lever arm on myosin that is organized in a very clever way through the course of evolution so that domain closure driven by ATP binding can be coupled to actual real mechanical work that you can observe. So that is just one simple example, or the movement of the piston, but those are simple, and I think the myosin is sort of a cleaner example of how a chemical reaction, in the case of myosin ATP binding, which does release heat, by the way, does work. by moving the lever arm of myosin, which then can be connected to other massive things in the real world, right? So this is our basic model. We have a chemical reaction that releases heat. Because it releases heat, the delta H is less than 0. And in addition, the reaction is somehow coupled to work. So for the moment, let's just imagine that that work is some mass attached to the lever arm of myosin, and in the chemical reaction is the binding of ATP to myosin, which again does actually release heat. Okay, so the first law says that the energy is conserved. Heat is work, work is heat, and Newtonian energy is conserved. And the first law then will say that the heat released to the environment, which generically in thermodynamics is referred to as a bath, a heat bath. There can be a little bit of subtlety there, but for the moment, let's just say, for the moment, we're going to call the heat bath. Well, for the moment, the heat bath we're referring to is simply the solution in which the reaction is happening. I will come back to that later. And so the heat released to the environment is going to be negative delta H. Why negative delta H? Because when heat is released, our convention is that heat release is a delta H less than 0. Therefore, negative delta H is going to be the amount of heat released to the bath. And again, the bath is simply the solution. In this case, the bath is the solution in which the myosin is located. Because energy, the first law, heat is work, work is heat, energy is conserved. If there is work coupled to the binding reaction, of course, heat is work, work is heat, they're both energy. The exact amount of work done by the reaction has to be subtracted away from the total heat release to get the net heat release, not including the energy that goes into doing the work. Okay, so the Gibbs relationship, we're working deriving the Gibbs equation. The Gibbs relationship is what we have seen before, that the change in the entropy of the heat bath is essentially the amount of heat released divided by temperature. So that's just written here, right? This is the net heat release when the reaction is coupled to amount of work W divided by temperature. This is the entropy increase in the bath, which again, to be specific, in the case of a myosin molecule in a test tube, the bath is the solution in the test tube. Before I go on, this is another area where the Carnot cycle is just hugely confusing. Let's not talk about it now. For the moment, I'd recommend you put it out of your mind, and if you have questions about that, let's consider them separately. Right, so simply at the moment, we have a chemical reaction, let's say ATP binding to myosin, and triggering this domain closure, which moves a lever arm. The heat released in the course of that domain closure, that ATP binding linked to domain closure, that biochemical binding reaction, is negative delta H, but the movement of the lever arm does some work. We subtract out the work to get the net heat release. The net heat release divided by temperature is the entropy increase in the solution, which we're calling the bath. Okay, the second law says for something to be spontaneous, the total entropy change has to be greater than 0. And so so where do we get the total entropy change? Well, in addition, so one important place, one important component of the entropy change is the entropy change in the change in the entropy of the energy distribution, which is essentially the entropy of the heat distribution in the solution, which we're calling the bath, right? So one very important source of energy is again, the change in the entropy of the heat configuration, or the probability of the heat configuration, the number of ways you can arrange the heat when the heat is released to the solution, which we are calling the bath. And because energy is conserved, this is the only way that energy will ever influence spontaneous change. Energy being conserved can never make anything happen or not happen. It's always entropy. Energy is always moving around as a slave to entropy. When you're looking at spontaneous change, and again, the equilibrium point is the systematic lack of a spontaneous change. So it is controlled by the laws controlling it, by the second law of thermodynamics, which controls spontaneous change. The only way energy is ever going to affect that is by the release of heat to some bath, which changes the entropy of the heat distribution in the bath. But that is always going to be one important source of entropy, the entropy change in the energy distribution in the bath or solution due to the heat release. So that's this term here. In addition to that, there can be other entropy changes during the reaction. These can come from a number of different sources. In biochemistry, an obvious source is going to be hydration and the hydrophobic effect. Those would involve changes in the number of spatial configurations associated with the state, the reactant or product state. And then there are others. I actually misspoke in lecture the other day, and I said that if you have two molecules coming together to form a complex, I think I misspoke and said that the equilibrium constant, the concentration ratios, would not capture the change in the number of positional degrees of freedom. That was I was speaking too quickly there. What we're going to talk about in a moment about concentration ratios and to equilibrium constants, that actually does change cover the change in the positional entropy when two things become to one. But in addition to that effect, when two molecules form a complex, when they are separate, they are rotating independently. When they are together, they are rotating as one. So there is actually a loss in rotational configurational possibilities, and so there is essentially a loss in rotational entropy. That would be another contributor, the delta S0, and the hydrophobic effect entropy would also contribute to the delta S0. So what we've done here is we are summing the intrinsic entropy changes in the course of the reaction and the entropy change due to the heat release. This now becomes like quite trivial algebraically. All that I've done here is multiply through by absolute temperature. By doing that, we get rid of the temperature. We move the temperature from being in the denominator, which is a somewhat inconvenient place to have it algebraically, especially if you're using these equations practically in the lab. Things in the denominator, particularly large numbers in the denominator, are always a bit harder to wrap your mind around than they were in the numerator. So essentially, we're just getting the temperature out of the denominator. What we get to at this point is that T delta S minus delta H minus W has to be greater than 0. And of course, now this is trivially rearranged to T delta S 0 minus delta H 0 is greater than W, the amount of external work coupled to this reaction. And if we multiply, let's distribute out the negative sign here in the next step. Now I am going to define delta H minus T delta S, the Gibbs free energy. You've seen this before, and hopefully now it's crystal clear where it comes from. So this gets us to really one of the critical components in deriving the Gibbs equation, and furthermore a direct explanation of why the free energy is why the energy available to do work is delta H minus T delta S, which we have defined as the free energy, right? So what we get here is, right, we distribute out the negative sign, we get negative delta G0 has to be greater than the amount of work done. Of course, if that's true, the work done has to be, right, we then multiply through by -1, and we get the work done has to be less than negative delta G0. Remember, favorable, like favorable energy, right? Well, like an exothermic reaction releases heat, that's delta H, the magnitude of the sign of delta H is less than 0. Favorable free energy is also less than 0. So, right, if the reaction is happening spontaneously, the delta G is less than 0. And so favorable delta G is less than 0. So negative favorable delta G will be a positive value. This is saying the maximum work that can be done is less than or equal to that positive value, which is negative the delta G. And so so what this means is that the reaction, well, if you just think back to the starting point, we're assuming this reaction is happening spontaneously and has intrinsic entropy and enthalpy of delta H and delta S, and we're assuming it's doing an amount of external work W. What this says is that the amount of external work that has been done is got to be less than negative the standard free energy. And again, if you look back at what's happened here, this is derived from entropy terms, exclusively from entropy terms. And so really this is capturing an entropy effect. The only way the work is entering it is that any work is done because of the conservation of energy, that much less heat is released. And so the conservation of energy means, in the first law, heat is work, work is heat. These are both Newtonian energy, which are never created and destroyed, but only moves around. The maximum amount of work that can be done by the reaction that is something essentially external to reaction, the amount of external work that can be done is going to be delta G, negative delta G0, right? So this does reflect the free energy is the maximum amount of work that can be done by the reaction, right? The meaning for the react, and so right, this comes back to what does it mean work can be done? Work can be done means the physical system will proceed spontaneously to do the work. Right? And so again, the work that can be done is a question of spontaneous change. What work can be done spontaneously? The work has to be less than the negative delta G0 for the physical system to spontaneously move forward and do the work. So it is the energy available to do work, but that is implicitly the energy available to do work spontaneously, and this is all about, therefore, spontaneous change. And so the Gibbs free energy represents an energetic phrasing, as it were, of the second law of thermodynamics. Technically, this is at constant temperature and pressure, and there will be situations in which that's important. For when we're doing biochemical and biophysical lab work, and usually cell biology and molecular biology, we are doing it at constant temperature and pressure. So that's in the background, but that is, that is an important caveat. Okay, so that explains how free energy is defined, where it comes from, hopefully makes it clear what it's about. Okay, so the next thing we're going to do is sort of skip ahead a bit and now try to ask how this is, so this is the standard, right? So we've just derived the standard free energy as which will, right, the standard, what we've done here is we've shown the standard free energy is the maximum amount of external work that can be done by the reaction, we have defined the delta G0, the standard free energy, as delta H minus T delta S, which essentially captures the intrinsic entropy change in the course of the reaction, the entropy change due to the heat release or absorption by the reaction, and in this case we have put them together in a way that will give us the maximum amount of work that can be done by the reaction. But now to find out the relationship between the standard free energy and an equilibrium constant, we have to now think about how concentration relates to all of this. And we have done we've established the foundation for that before, so at the moment I'm not going to cover those slides again, right? We have been through these slides before, and we've been through these slides before, and so I'm not going to, in this screencast, go back and look at them again. It does make the critical, right, but the critical points are that as you increase the concentration of a solute in a solution up to the 50% mole fraction point, as you put more molecules in, starting with a solution, a solvent that is all one kind of molecule, as you add and then increase the amount of another molecule in there, the number of arrays you can arrange those molecules in whatever volume they're in increases consistently until you get to the 50% mixture point. And so the entropy of the spatial configuration continues to increase until it's a 50-50 mixture. But the gain in the entropy, which is the slope of this absolute entropy curve, the gain in the entropy is, although remaining positive up to the 50-50 point, the magnitude of the gain of the entropy perpetually declines as you get up to the 50-50 point. Similarly, if you plot the heat entropy, right, the entropy of the heat distribution in a solvent or a solution, in this case it's actual real thermodynamic data just on water, as you increase temperature, right, although temperature does not measure heat, to go to higher temperature you have to put in more heat, more ways to arrange the heat, higher entropy of the heat distribution. However, the gain in the entropy of the heat distribution, which is once again the slope of this line, although it remains positive, as in this case all the way up to, whatever temperature you can get to, higher temperature, always more heat going in, always more ways to arrange the heat, but the gain in the number of ways to arrange the heat declines monotonically with temperature. That is the Gibbs relationship, and so there is essentially parallel behavior between the entropy of the spatial distribution and the entropy of the heat distribution. Okay. Anyway, when we what we derived earlier, which I am going to briefly note before we go on to relating this to a chemical reaction. We have previously derived we've gone through this heuristic derivation that shows that the entropy gain, it shows that mathematically we can describe the entropy gain in the spatial distribution when the concentration of a solute is increased as equal negative r times the natural log of the solute concentration. Of course, the very simple characteristics of the logarithmic function means that negative r ln n is equal to r ln 1 over, I'm sorry, negative r ln concentration of A is of course going to be equal to r ln of 1 over the concentration of A. And so this is the fundamental equation describing the change in the entropy of a solution. I'm sorry, the change in the entropy of the spatial configuration of a solution as you add a little bit of solute to it at an existing solvent. I'm sorry, this is the gain in the entropy of the spatial distribution of a solution when you add a little bit more solute to it when the solution is currently at has a solute concentration of A, right? So if you have a solution where the current solute concentration is given by this symbol, concentration of A, if you add one more molecule of solute to it, the gain in the entropy of the spatial configuration is going to be R ln 1 over concentration of A, which is negative R ln of A, this is essentially measuring the gain in the entropy of the spatial distribution for addition of a single molecule to the solution, but it has been multiplied by Avogadro's number to put that gain on a molar scale. We've discussed that before. These processes are rightly, the entropy is a state function. If I put one molecule in, I will get a gain in entropy. If I take one molecule out, I must get exactly that equal and opposite loss in entropy, and therefore as concentration is increased by one molecule, you get a entropy change. Well, if you increase the concentration by one molecule, the entropy change you would get. So the entropy change you get for increasing the concentration by one molecule multiplied by Avogadro's number is negative R ln A. Concentration of A, and on the other hand, if you take a molecule out, the entropy loss that you will get will be R. The entropy loss you will get by removing that molecule multiplied by Avogadro's number is going to be R ln A, right? So these are obviously just one is the negative of the other, and that does reflect the fact the entropy is a state function. Right? So a solution at any given concentration is going to have an entropy value. If we put in another molecule and its entropy increases, and then we remove that molecule, its entropy has to go right back to where it was, and so these have to be equal and opposite. Okay, we've also covered that before, but just to very briefly review that. Now this is we're getting close to to being able to relate this now to the free energy. And so to do that, what we're going to do is consider, I'm not going to, I could do this same counting exercise, going R plus L goes to RL. I'm going to leave that actually for you to play around with. The math would be exactly the same, effectively. In that case, the point would be, right, in this case, what we're considering is a unimolecular transition. We have spoken about one particular unimolecular transition extensively already in the class, right, which was the inactive receptor going to the active receptor. That's a model of a protein conformational change. That is one example of a unimolecular reaction, an important one when we're doing biochemistry. So the idea here is we have one molecule of A going to a molecule of B. Again, these, you could consider these R and R star. In the receptor-ligand binding interaction, we would have R plus L goes to RL, but the math that would in the end, there'd be additional terms, but it would be the same math. You'd be reducing the number of R molecules by one. You'd reduce, if it's one-to-one binding, you'd be reducing the number of L molecules by one every time the reaction happens, and that would be coupled to increasing the number of RL molecules by one. So the same math I'm going to do here with a trivial extension would extend to R plus L goes to RL. Or to R plus 2L goes to RL2. These would all be trivial extensions of the math. So let's just go through this like sort of simpler one to look at in terms of the notation, right? And so what's happening here is I have now, in the same way I previously accounted the number of ways I could arrange the A molecules in this box, I am now going to count the number of ways I could arrange the A and the B molecules. And of course, the first time I put in either molecule, would there be n choices, then would be n minus 1 choices, n minus 2, blah, 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 until I put in the n minus A minus B plus 1 molecule. So when I put in the last molecule, there would be n minus A minus B plus 1 choices. When so I would have a continuing product that goes from n to n minus A minus B plus 1, and that is conveniently represented by n factorial over n minus A minus B factorial. But that counting exercise counts the number of ordered sequences, which I would put in A and B, and we don't care about the order because when they're in a particular position, that the order does not create, changing the order of filling the boxes does not create physically distinguishable states. So to get the physically distinguishable states, we need to divide by the number of orders in which we could fill the boxes with A in them, divided by the number of orders in which we could fill the boxes with B in them. This is exactly the way the math that we've done before, and so this reflects the entropy of the reactant state. Now, when 1A goes to 1B, well, this goes up by 1, that goes down by 1. Fine, that cancels out. This goes, A goes down by 1 and B goes up plus by 1. And this is the same counting exercise we did before, but now rather than just looking at the A concentration, looking at an AB conversion, right? And now I'm not going to even, I will let you step through the math yourselves, but this is sort of trivially done. And what you get to in the end, what you rapidly get to when you simplify this is the change in the entropy of the spatial configuration. And now remember, what we have done here is we have had one reaction happen. One molecule of A has converted to one molecule of B, right? And so when that happens, what you get is the change in the entropy of the spatial configuration is going to be K, the Boltzmann constant, times the natural logarithm of A, the number of A molecules, over B, the number of B molecules, right? But now if we simply divide the top and the bottom, the numerator and denominator, by n, the number of boxes, that gives us the mole fraction concentration, because we're dealing with large numbers, B plus 1, right? Like even for 1 microliter of solution at 1 nanomolar, right? That's, 10 to the 6 minus 6 would be a microliter, 10 to the minus 9 nanomolar, that's 10 to the minus 15, but an Avogadro's number is 10 to the minus 23. Even 1 microliter of a solution at nanomolar concentration, it involves about 6 times 10 to the 8th molecules. 6 times 10 to the 8th compared to 6 times 10 to the 8th plus 1 is insignificantly different. And in this case, therefore, we can have a very good approximation of the entropy change as K times the natural log of the concentration of A over the concentration of B. And note that all these are mole fraction units. For a dilute solution, as we've said before, the mole fraction is linearly proportional to the concentration, the molar concentration. The proportionality constant will be the same for both A and B because they're both in the same, whatever physical configuration here. And so in this case, the same proportionality constant multiplied in the top and the bottom would give you the molar concentrations. And in this case, this actually works perfectly mathematically with no hidden complications. And so that is the change in the entropy of the spatial configuration when this unimolecular reaction happens to one molecule. 1A goes to 1B. What we're going to do from there is basically just multiply by Avogadro's number. And again, this can be slightly confusing, but the bottom line is we're looking at the change in the entropy of the spatial configuration when the reaction happens once, and simply putting it on a molar scale by multiplying by Avogadro's number. K, the Boltzmann constant, times Avogadro's number is the ideal chaos constant, which has units of mole per degree Kelvin. Okay, so now, what we're going to do is connect this to the Gibbs relationship, and what I'm going to do is calculate the free energy in the course of a reaction, where as opposed to the standard free energy, which is simply looking, right, what we derived earlier was the standard free energy. That was based on the enthalpy and entropy changes for the reaction happening once. That's like one reaction cycle. It gives you the standard enthalpy and the standard entropy. Now what we're going to do is we're going to take that one reaction, we're going to actually take that sort of abstract system of a reaction happening, and we're going to actually put that reaction in a specific context, in a specific solution, where the products and the reactants are at specific concentrations. And when we do that, in addition to the intrinsic entropy change in the course of reaction, we're going to have additionally this entropy change due to the change in the entropy, the spatial configuration when a molecule of A goes to a molecule of B. And so, right, delta G equals delta H minus T delta S. In this case, there are two contributors to T delta S, the standard intrinsic entropy, the intrinsic entropy, the standard intrinsic entropy of the reaction, plus the entropy of the concentration change. But now for this unimolecular reaction, we have explicitly calculated the entropy of the concentration change, and it is negative, right? And it is, of course, the delta S is R ln concentration of A, concentration of B. In this case, right, A is the reactant, B is the product. So we get delta G for the reaction, the free energy change in the course of the reaction at these specific concentrations now is going to be delta H minus T delta S, which is standard enthalpy minus temperature times the standard entropy. So that is the standard free energy of the reaction minus RT times the natural log of A over B, which is the ratio of reactant to product. So this is basically an equilibrium constant. Again, we've derived this just a few minutes ago in this screencast, and right, these are all the and so now to sort of refocus the context, right, the delta G0 is basically all the thermodynamic factors but the concentration change. We're considering the concentration change separately because that's in practice what we need to do when we want to figure out what was going on in an actual solution, in an actual experiment. But conceptually, it's really quite straightforward. We have simply divided the intrinsic entropy and enthalpy changes in the course of the reaction, which means the entropy and entropy changes happen associated with this reaction happening once, like one molecule undergoing the conformational condensation. In a moment, we'll look at one receptor and one ligand molecule binding to one another. The standard free energy is capturing what happens when one molecule goes through when one set of molecules goes through one reaction cycle. And then, however, the numbers we're going to work with are always going to be those entropy and enthalpy changes multiplied by Avogadro's number. So in this point, the free energy of the reaction is going to be the standard free energy of the reaction, which is what happens when one molecule goes through this, undergoes this unimolecular reaction, minus RT ln of the concentration, the ratio of the reactant and product concentrations. Okay, so now let's extend this to our canonical equilibrium binding equation, reaction. And right, we've looked at this before, and we've talked in detail, and you've worked problem set with kinetic cooperativity, and so you should understand that in detail. Stoichiometry, we've punted consideration of that down the road, but we will be talking about that in very short order. So for the moment, we're still going to just consider that. We're going to keep that. That's going to be in the equations so that all the equations to the slide deck match one another. But for the moment, we're still ignoring the S and just considering it as part of this. For the moment, we can consider as part of the symbol for the receptor is SRF, the free receptor SRLN, the complex. We'd previously established that and you've now worked with this extensively, that the kinetic condition for equilibrium is that the forward rate, Ks SRF LF to the n, is equal to the reverse rate, Kr times SLRN, right? And then simply rearranging this, we get in a very straightforward way, which we've done before and worked with extensively at this point, we get the ratio of the reactant concentrations, SRF times LF to the n, to the product concentration is what we now are going to represent by Kd to the n. And for a given reaction at a given temperature in a given buffer environment, this is a constant that is what you will observe when the system hits equilibrium. So no matter what reactant and product no matter what reactant concentrations you start with, you can change these to whatever, and when this reaction comes to equilibrium, the ratio of the reactant concentrations to the product's concentrations will be a dissociation, will be a constant, and we're calling that constant Kd to the n, and you have already worked with that quite extensively. So now how does this relate, right? So this was, right, the kinetic condition for equilibrium. Now we got to relate this to the thermodynamic condition for equilibrium. And doing that will immediately give us the Gibbs relationship. Okay, so right when you hit equilibrium, the total entropy change has to be 0, because equilibrium is not some random stationary point. It is the point where the tendency to go forward exactly equals the tendency to go backwards, and that means the entropy change in the reaction has to be exactly 0. So to figure out that point, now we previously looked at the kinetic condition for equilibrium. It gave us this. Now we're going to look at the thermodynamic condition for equilibrium, which is that the total entropy change as this reaction cycles forward once or cycles backwards once, the total entropy change has got to be 0. So we're going to add up the entropy change due to the concentration change, the entropy change due to the heat release, and then the intrinsic entropy change, and that's going to give us the total entropy, and that has to be 0. And so so we're going to substitute the intrinsic entropy change as delta S0. The entropy change due to the heat release to the solution or the bath is negative delta H0 given our sign convention over T. So we've already established these terms and these principles, and now so what we're doing is and so remember, these are now the entropy and enthalpy changes in the course of a single cycle of the reaction, right? So a single, n ligands in one receptor making the SRLN complex. The enthalpy and entropy change in the course of that single cycle of the reaction are captured by the standard enthalpy and the standard entropy, and when we combine them, we will get the standard free energy, which reflects intrinsically what's going on when the reaction happens once. In a real system, we are now going to also have to add in the entropic effects of the concentration change, which we have just been deriving, and that will give us the total entropy change. And so in the equilibrium situation in a solution, the sum of all of this has to be 0. Right, and so now this becomes fairly, again, trivial algebra. We're going to multiply by absolute temperature. The main reason being to get the temperature out of the denominator. So that will give us T delta S concentration, and then we're going to move this to the other side of the equation, and so that's going to be delta, negative delta H moves over, is going to be positive delta H times T is just going to be positive delta H0, and then here we're going to multiply by T and move to the other side of the equation, negative T delta S0, right? So this simple addition of all the sources of entropy rapidly gets us to absolute temperature times the entropy change due to the concentration change is equal to the standard enthalpy minus absolute temperature times the standard entropy, which is, of course, the standard free energy of the reaction. The previous slide, we didn't directly derive what the entropy change was in the course of this reaction, but note, for a simple A to B reaction, sorry, 2 slides back, the simple A to B reaction, right, we got the entropy change is going to be negative RT reactant over product concentrations, which means, negative RT reactant over product concentrations. Again, you could do this same counting exercise with R plus L goes to RL, or R plus 2L goes to RL2, and you would get a concentration ratio term that looks exactly like that. And again, I'm going to leave you to do that simple exercise, which, however, is very straightforward. And so that brings us down here, what we're getting at this point, right, is then going to be the standard free energy of the reaction is going to be T times the entropy due, the change in entropy due to the concentration change, and that is going to be RT times the natural log of LF to the n SRF over SLRN, right? And so this is the concentration ratio. This is the exactly analogous concentration ratio term to what we just derived for the unimolecular A to B reaction, simply extended to treat this somewhat more complicated reaction stoichiometry. But the same math would rapidly get you exactly right here. And so what you're getting at this point is then delta G, right? But what is this concentration ratio? Well, when you've met the kinetic condition for equilibrium, this concentration ratio is, of course, Kd to the n, right? And so what we get is the standard free energy of the reaction is equal to RT ln Kd to the n. The natural log of Kd to the n is, of course, n times the natural log of Kd. And so if we divide through by n, we get the standard free energy per ligand molecule, right? Because if there are n ligand molecules binding, we divide through by n, and we get the standard free energy per ligand molecule. The standard free energy for a ligand molecule is simply going to be RT ln Kd, and this is the Gibbs relationship. And so what does all this mean? Well, so what have we done? Like, let's have a one-sentence summary of what we've done. What we've done in the end, right, like the equilibrium point is determined by the second law of thermodynamics, because that is the point at which the reaction does not go forward, right? If there were an entropy gain to be had from going forward, the reaction would go forward. If there were an entropy gain to be had from the action going in the reverse direction, it would go in the reverse. The only time when the reaction hits this stable point is when there is no entropy change. And that will systematically cause the reaction to stay at that point because the system will have maximized its entropy. And so that condition of maximum entropy means that all of the entropy changes in the course of the reaction have to add up to 0, and that's because when the reaction goes forward or in reverse, there cannot be any entropy change if you've hit the equilibrium point. When we impose that thermodynamic condition for equilibrium, what we see is that at equilibrium, the entropic consequences of concentration change are exactly balanced by the intrinsic entropy changes during a reaction, which are captured by the free energy. The standard free energy, delta G0, which is given by delta H minus T delta S. So this is yet another situation where, all of the algebra involved in, calculating the concentration, the entropy changes due to the concentration change, that's slightly more advanced algebra. Other than that, the algebra involved in this is really quite trivial, but there's a lot going on here, and the concepts are not trivial. And getting the factors to fit together in the right way is also not trivial, and it naturally will take a bit of time to wrap your heads around all this. But you should be able to, in one sentence, concisely summarize for anyone who asks you, where the hell does the Gibbs relationship come from? Explain that what the Gibbs equation is telling you is that at the point of chemical equilibrium, the intrinsic entropy changes in the course of the reaction due to both any actual entropy change plus the entropy of the heat release. Those sum of all the intrinsic entropy changes, including the entropy change from heat release, is exactly balanced by the entropy change, the entropic consequence of the concentration change, and that is what establishes the equilibrium point in a solution. So that's we'll go into that now. So that is sort of, let's say, the full story, as it were, and what I'd like you to remember about the meaning of the Gibbs relationship, which is, of course, in the conceptual content of the Gibbs equation, which then, of course, is paralleled by its mathematical derivation, which again is algebraically very simple, although this is by no means conceptually simple. Okay, so that gets to the end point about that. I guess I just want to sort of add one little addendum to this, which I will do by scribbling on this screen here. Where's the pen here? Yes. So, Jinyue has asked me about the Carnot cycle and how all of this relates to the Carnot cycle. Carnot cycles are extremely confusing. The nomenclature is confusing. The physics of it, even, I think, are much more complicated than what I just talked about. So I'm not going to go into detail about that now. But I am going to talk about two things that are I'm going to just talk about 2 points that are related to explaining that Carnot cycle mess. but that are directly applicable to what we've just talked about, and also applicable, relevant to anything where you're considering concentration, including the problem set on solubility. And so this is sort of whatever, really a question of mostly sort of jargon, but there's a little bit of physics in it. And importantly, jargon, good jargon is stuff that is very clearly defined and that makes the physics easier to understand. That would be one of my complaints about the Carnot cycle, the way that it's taught. I think the jargon is not used in a completely consistent way, and I'm not convinced it makes it easier to understand. But anyway, I want to just clarify some points of jargon that hopefully will also make it easier to understand the physics, the physical chemistry that we're talking about. So let's just say we have a test tube. As I'm doing this, you will see why I have not pursued a career as an artist. Anyway, so we have a test tube, right? So it's supposed to be sealed to the outside world. And let's just say in this test tube we have some solution. And let's just say that in this test tube we have our reaction going on. And I'm just going to schematize this way. But of course there would be, in a real solution, many molecules undergoing this reaction. And let's say in the course of this reaction there is some heat release. And let's call that heat release delta H0. And that will have the sign according to our convention, meaning if it's a heat release, the delta H0 will be less than, delta H will be quantitatively less than 0. If it's for an exothermic reaction with heat being released, delta H is less than 0. With its endothermic reaction with heat being absorbed, delta H would be greater than 0. And but the important point is, and a simple way to sort of understand where the heat could come from would be simply an electrostatic potential interaction here. If these things are oppositely charged, when they come together, they'll go to a potential energy state. The first law will then say, well, whatever that reduction in potential energy is, that much heat is released to the solution. Prying them apart, we would have to take that much heat out of the solution. The important point here is that heat is going to this solution. The solution is generically referred to as a bath. Heat bath. In this case, the heat bath is the solution. There are situations in which people will use that term bath to mean something different. And in the Carnot cycle, basically when people use that term, they're using it to mean something different. And again, for the moment, just ignore that. So in this case, the heat bath that we're talking about is the solution. The heat that's being released in the course of the reaction is going into the solution. So what we're talking about here is, again, all of the heat remaining internal to the system. So the way that we're talking about this and setting up and analyzing it, right, the basic idea is that this is completely insulated from heat exchange with the environment. So all of the heat and all of the heat energy that is released or absorbed in the reaction is staying internal to the system. So this condition is called adiabatic. Again, terms that are clearly defined, terms should not be defined unless they help you specify and understand things. Terms that are clearly defined should be are a valuable aid to understanding and to pedagogy. Adiabatic means no exchange of heat from the environment, right? So this is an adiabatic movement of the heat. In the solubility problem set, we are also considering that as an adiabatic system. In the urea dissolution experiment that we did in the class, in that case, after a period of time, the solution warmed up and there was heat exchange with the environment. But as the reaction was happening, the heat exchange is slow. So as the reaction is happening to a first extent approximation, sort of moment to moment, that dissolution reaction of the urea was adiabatic. The heat was being transferred in that case from the urea crystal to the bath or the solution, right? And there was no heat exchange with the environment moment to moment. Later on, it exchanged, but it didn't exchange. When you're working the problem set, you are assuming things are under adiabatic conditions for the solution. Now, on the other hand, when we talked about free energy, we talked about the reaction being coupled to work, right? So when you're talking about systems like this, the work essentially can be external, right? The myosin lever arm, like we could have a myosin molecule pinned down in here in some way, and when ATP bound, its lever arm could be connected to something else that would pull on something outside of the system. This is, in effect, the way your muscles work, right? So the work could potentially be external, and it could be bidirectional. When the myosin lever arm closes, it can do work on the something external to the system if you have it set up mechanically the right way, which your muscles do. On the other hand, we could also then do the reverse process. We could use the external work to pull the myosin domains apart, right? So work could go into and out of the system. And when we derived the expression for the free energy and showed that the standard free energy is the amount of energy available to do work, that was basically consistent with this, right? We were saying some work was going to be done, and I didn't say it explicitly there, or maybe I did, or maybe I didn't. I don't remember. But the bottom line is the work could be external to the system. The heat remains internal to the system. The work could be external. Heat is work and work is heat, but according to the first law. But what we're doing now is we're breaking them down. We're considering the heat transaction, as it were, separately from the mechanical work, as it were. As I've discussed it, it's mechanical work. And right, so we're separating out the work being done by the reaction from the heat transaction involved in the reaction. The system we are considering is adiabatic, meaning we're not trading heat energy into or out of the system, but the work that's being done can be external. Now, for the solubility problem set, and frankly, for almost everything we're doing this term, coupling to external work, we're not going to be coupling to external work, but in principle it could be, and the derivation of the free energy expression, is such that would cover the externally done work. Why am I mentioning this now? Well, I think people have asked me questions about where the heat is going, even when we're talking about simply the solubility equilibrium. In all of the problems we're working on, the heat is remaining in the system. The system is adiabatic. Heat is not being exchanged. No heat energy is moving out of the system or moving into the system. On the other hand, we have allowed for the coupling this to external work. And so work could be done on something external to the system or move into the system, but the heat is all internal to the system. When heat is released in the course of the reaction, it is being distributed anywhere that heat can go in the solution, which in this case is the bath, the thermal bath, and it is increasing the entropy of the thermal bath. When energy moves, if the reaction involves going to a higher potential energy state, the heat has to move from the solution, the bath, into the reaction. That has to take heat out of the bath. That will lower the entropy of the heat distribution in the bath. So the problems that we're working on, the heat exchanges are always internal to the system. The system is always, therefore, quote-unquote, adiabatic. Work, on the other hand, can come in and out of the bath. Now, were I to describe the Carnot cycle, which some of you have asked me to do, and I will do offline, these same principles would essentially apply. There's just way more complex things going on there. I don't want to talk about it now. But anyway, these definitions would also apply in that case, and then also I think this helps sharpen the focus on where the heat is moving around in the problems that you're actually going to have to work. Okay, so that covers the objectives that I set out at the outset. We want to derive the Gibbs equation, but we also want to understand exactly where it comes from. What is the conceptual foundation of that? What is the basic fundamental physics of that? The fundamental physics of it is that at the equilibrium point for chemical reaction, the intrinsic enthalpy and entropy changes, which are those that take place in each reaction cycle, are exactly balanced by the entropic changes associated with the concentration changes as reactants go to products or vice versa. So we have covered that, and hopefully in the process we have enlightened you as to where it comes from, how the pieces fit together, and importantly, set you up to apply these concepts to real-world problems, at least biochemistry and biophysics problems.